Thank you, Vasan. So, like you said, the talk is on the determination of tissue properties from optical signals. And there are several groups, it's kind of the basis of our work is to diagnostically determine the constituents or the composition of tissue. So this is done on several spatial scales. Giacomelli and his group are looking at determining the size and shape of single scatterers, so we're down at that level. Sylvain Joux and his group are looking at thicker tissues, finger, and determining the optical properties of those. And then even thicker tissues like breasts are analyzed, and optical tomography is used to determine the distribution of the absorption and scattering. So these problems span all spatial scales, and they're looking at 4 different constituents of the tissue. And because of that, the computational models have to span the different spatial scales as well. Giacomelli's group uses Me and T matrix scattering phase functions, analyze the tissue using those. For thicker tissues, Monte Carlo methods are used to solve the radiative transport equation. Vasan showed a lot of nice results which show how well delta P1 does in solving the radiative transport equation for certain problems. And then, of course, standard diffusion has been utilized quite a bit to solve the RTE. So in this talk, I hope to describe the chi-squared minimization. This is the heart of all inverse problems, the assumptions that are made about its formulation, the different components of that equation, and considerations that should be taken into account when you apply different models. I'll look at some optimization methods, table lookup, a direct search, and some gradient based. And this is just an overview of those methods. I'll also go over the PMC-DMC. This is a gradient-based stochastic inverse model that we use to determine optical properties in a layered system. And then briefly go over optical tomography. And then I look at some case studies looking at reflectance versus source detector separation, and then reflectance versus spatial frequency and wavelength, just to give you an idea of, with an actual problem, what the chi-squared space looks like. So you've seen this diagram quite a bit in different forms throughout the week, so I'll go over it pretty quickly here. We have the forward problem, in which we have as input optical or physiological parameters, optical absorption or scattering, and you feed that into an optical model and outcome predictions of your measurements. The inverse problem is taking those measurements, using a model, and then determining what the optical physiological parameters are. And as Jerry mentioned earlier, the forward problem is well posed. A unique solution exists. But often the inverse problem is ill-conditioned. And that means that several sets of optical or physiological parameters could produce the same measurement predictions. And so determining the inverse problem is going to be difficult. So the inverse solution is affected by your choice of your model function, the parameters that you're trying to look for, and the type and quality of the measurements. So in the chi-squared minimization, the goal is to fit a model function, like SDA or Monte Carlo, all those different kinds of solution, model function with adjustable parameters to a set of measured data. So suppose you have M measurements, and I identify them with a little y hat, so 1 through M of these measurements. And a model function, it's a y without the hat, with P adjustable parameters. So those are your optical properties or whatever characteristics you're looking for. Then the goal is to find a unique vector A is of length p, the number of parameters, if it exists, that minimizes this chi-squared function. And it is the sum over all the measurements of the quantity, the difference between each measurement and the model prediction with the current set of parameters divided by the standard deviation of the measurements, and that quantity squared. And Jerry mentioned earlier that this is a weighted chi-squared. The reason why it's weighted is that in the denominator you have the standard deviation of the measurements. So when a particular measurement has a large standard deviation, that contribution of that summand to the total summation is going to be smaller. And those that have a smaller standard deviation, those measurements will get amplified. So that's why it's a weighted chi-squared. Now, the formulation of this chi-squared equation derives from the maximum likelihood estimation. And there are two key assumptions about that formulation. First of all, that the measurements are mutually independent, and that the measurements are normally distributed about a mean that is the model function. So those two things, that's in a perfect world. Now when we actually solve inverse problems, these things are violated, and I bring this up because that may be why your inverse solution is having problems. So let's look at the components. In the blue, the y hat are the measurements. And you'd like to have as many measurements as unknowns. You know, as we have solved AX equals B problems, that's kind of a fundamental rule. Let's have as many equations as unknowns. And you'd like it if the measurements were in places, locations, or times that they're sensitive to the changes in the parameters. We've seen a lot of plots this week about, David showed some plots about his spatial frequency domain and the different ways, the sensitivity to mu A and mu S changing. And so you want to make sure that you're placing your measurements, or you're choosing your measurements such that a small change in mu A or mu S or any parameter that you're looking for actually invokes a large change in the measurement, so that that measurement is sensitive to that change. You want to consider, is there redundancy in the measurements? That's getting back to the assumption of the maximum likelihood. It's possible that you have more measurements that you need. You could do with far fewer and still obtain the same answers. And David talked a lot about this. How are the measurements calibrated? So those are the kinds of the considerations you have to think about when you're looking at the measurements that you're choosing. For the model function shown in green, is this model function accurate for the measurement domain? We saw that for the standard diffusion approximation, we need that scattering, mu S prime, is greater than mu A, much greater than, there's a lot of scattering in the problem. It also applies to problems in which you're not too close to the source. So you have to consider that. Is the model function sensitive to the changes in the parameters? So just like SDA, it's based on mu S prime and mu A, but it has no knowledge of G. So you have to make sure that you pick your model function so that it can give you back the information that you need. You'd also like the model function to be able to provide a prediction at a given A vector fairly quickly, because a lot of times these optimization methods are iterative in nature, and so you want, as you're trying to search for the optimal solution, you want to be able to produce a prediction at varying A values pretty quickly. You'd also have to consider, do the model predictions need to be integrated to match the measurements taken? Do you have a detector that is of a finite diameter and you're using SDA that gives you a point reflectance solution? You might have to integrate that over the the spatial extent of the detector. And do you have this denominator that makes it weighted? Do you have an estimate of the measurement error? If not, then it just reduces to the chi-squared without the denominator, and that can be minimized as well. But if you do have that information, like I said, it does help in the optimization. So we've seen, oh, Tom, did you have?
So more of a curiosity than anything, but why do we use the square of the residual chi-squared? Why not just the absolute value of the difference as a minimization function, or higher orders, or some other more complicated function?
It's a good question. It falls out from the maximum likelihood derivation of the chi-squared, I think, but also it's measuring the distance, the distance from the optimal, the two, the measurements and your model function. And so, yeah, I think you definitely want to square. It's a positive, chi-squared is a positive value, so if you were to take away the square, that would not apply. So, I'm not sure if I'm giving the best answer there. It's a good question.
Jerry, do you have a comment on why the square is used as opposed to, say, an absolute value?
Yeah, I would comment that the chi-square distribution in statistics is a well-known distribution, and so people have adopted it conventionally, because if you have the assumptions that you need, the normality, then you will get a chi-square distribution for this measure of error.
It falls out from the maximum likelihood derivation.
So, chi-square distribution with so many degrees of freedom is something that's been studied to death, and so it is it's kind of a canonical way of getting errors. Gordon, you had a question?
I was just going to say a simple reason to use the square of the error is if you're summing over all your errors and you have positive errors and negative errors, then it's possible to still have a lot of errors and a zero sum. Whereas if you turn those into distances rather than vectors, then you see the total deviation. And that's a sort of hand-waving approach without going into, more detail.
There's other ways to quantify the error. It sounds like it's more of a statistical.
Yeah, and I think it.
Mine is moving on to like another question, so I don't know if you guys want to talk about. Oh, so for my question, I don't know if you'll talk about it, but for example, like what we were doing yesterday when we were trying to match like deoxyhemoglobin, hemoglobin to a chi-squared, do you do like each point for chi-squared, or do you fit like the entire function?
I'll show you an example,
Okay.
I think, and if not, you can ask it again after I show.
Okay.
Okay.
All right, thank you.
Sure. So during this week, we saw how you can choose different kinds of solutions for the different types of tissues that you're assuming the tissue to be. For instance, if it's homogeneous, very simple defined tissue that's homogeneous or layered, or say it has a sphere or simple inclusion, there are standard diffusion approximation analytic solutions for those types of there's types of tissues. But as you decrease the spatial scale or you increase the amount of absorption, then you need to go to higher PN solutions like delta P1 or there are other PN solutions that you could use. For very complex tissue definitions, then you'll need to go to a Monte Carlo method. You can consider the different measurement domains that you could consider different measurement domains. For instance, source detector separation, spatial frequency, time, temporal frequency, wavelength, or any combination of the above. And then consider the optical properties that you're trying to determine. Are they your absorption, scattering, G, refractive index, or are they chromophore concentration, or are they scatterer size? So all of these play a part in the success of your inverse solution. So I'm going to briefly review a few different types of optimization methods that I did a little literature search and found the different types that have been used for different types of optical property determination. You saw from David that he used a lookup table methodology in some of the results that he showed. I'll go over that. Levenberg-Marquardt is a gradient-based optimization method that's prevalent in the industry, and I'll go over that algorithm. Simulated annealing was used by Alexandrakis to determine the optical properties in a layered tissue. A genetic algorithm was used by Hilscher to determine mu A and mu S prime. And then you use the Simplex method in the integrating sphere exercise that you did yesterday. So in the lookup table, lookup tables are very nice in that they're very easy to generate. You take the parameters of interest. For instance, in David's, he took mu A increments. You take a range that's reasonable for the tissue that you're considering. So mu A increments and then mu S prime increments. And then you take your forward model and you generate this table at each of the increments. And once this table is generated, then you take your measurements, you use the lookup table, and I think I show it over here. So as David showed, he had a spatial frequency of 0.5 inverse millimeters here, and on this side, measurements of spatial frequency equals 0, and then along these lines are constant mu A, and along these lines are constant mu S prime. So he takes his measurements, whatever measurement over here for this spatial frequency, and over here, and finds the intersection. This happens to exist on a node, but if it existed in the middle, you would interpolate into there. And from there, you can very successfully determine your optical properties. Yeah, and I think I covered that. So one of the things that is nice about, as you see here, David pointed it out, these are nice and separate. There's no collapsing. We saw in the presentation, I think, from Rolf, there was a plot of reflectance and transmission based on albedo and the thickness of the slab. And there was this collapse of all of this grid down close to this region of the plot. And that shows how the uniqueness of solving that will be challenged in that range. So in this particular example of David's paper, you see how nice and orthogonal these isocurves are. So that's an easy one. Next one is simulated annealing. And in this algorithm, you set initial set of parameters. You get an initial guess of what your parameters are. And you determine your step size to the next update to those set of parameters based on this temperature T. There's a temperature cool down. This is where it gets its name from simulated annealing. So you determine it based on this temperature T, and if you decreased your chi-squared with that update to the parameters, then you accept and you move to that location, A plus delta A. But then if you increase the chi-squared value, then there's this probability function that sometimes you accept. And if you choose a random number and it is less than this probability function, then you actually accept moving to that update, and otherwise you don't. And you do this in a series of iterations, and during those iterations, you also decrease the time as you're moving along you have this cool down schedule until you're at the lowest T, and then you stop. So one of the things that's nice about this method is that you transition out of local minima. This is a schematic of what chi-squared space might look like. Here's a parameter, say we're looking for two parameters, A1 and A2. And for these different values of A1 and A2, the value of chi-squared is shown here. You can see that I'm trying to represent that the minima is in the red, and so there's a trough there. But the simulated annealing, what it allows you to do is that you might be moving, downward, because the chi-squared is going to get lower and lower and lower as you move downward. But you could get caught here in this local minima, and so once in a while it lets you percolate up and actually move to a region of higher chi-squared and get out of that minima to allow yourself to find the global minima. So that's one of the advantages of simulated annealing. But I need to say these two things. So the cool down schedule needs to be slow enough but not too fast, and that cool down schedule is user defined. I think there's some literature suggesting what that cool down schedule should be, but it's problem dependent, and so that could be problematic too, determining what the right cool down schedule is. And the way the algorithm works is that you start with your higher temperatures and you're actually moving a little more aggressively through chi-squared space, and when you lower the temperature, you're moving a little more finely. So next is the genetic algorithm. You take your parameters and you set a set of parents. So you have n parents that are randomly chosen. These are n combinations of this vector A. And you go through this reproduction phase in which you pair these different parents, n parents, in m different combinations. And then you take the average optical properties of the two parents and you form a Gaussian distribution centered around that average, and you create children. And then the children are evaluated as far as what their chi-squared value is, and we take the best n of those children and come around and they become the parents for the next generation. So this algorithm concept is survival of the fittest, because hopefully you're weeding out those parameters which are not genetically sound. So one of the,
Sorry. In this case, maybe we could just be a little more explicit in terms of optical properties. Are the parameters mu A and mu S?
Yeah, so say you're looking for mu A and mu S, then P1 would be mu A1, mu S1, and they would be randomly selected, and then P2 would be another pair, okay. P3 another pair.
They're completely randomly selected, or are they kind of intelligently selected?
Well, you hopefully intelligently. You don't want them to be negative, and hopefully you want them within, for instance, whatever wavelength that you're looking, you want to make sure, of course, the tighter you can bound the range that you're selecting them from, then the better. But, yeah.
I'm going to regret asking this one. What exactly is happening during reproduction?
The reproduction is just the pairing of the two parents together, and,
MUA1 with US2?
so this P1 is a pair. This P1 is a pair, MUA1 and MUS1, and this is MUS2 and MUA1. And so these two pairs get together, and you form the average of MUA1 and MU. So you get the average of the two optical properties, make a Gaussian about that mean, and then randomly select your child from that, for that MUA, and then same for MUS. And so, and then these children get evaluated in terms of chi-squared, and that's how the next generation gets formed. Yeah. Yeah, Hilscher had some good luck with this. Yeah.
You're running this optimization for only one wavelength for those optical properties, or are you doing it across the whole bunch? In other words, that A vector, how big is that?
That A vector could be across wavelengths. So you just kind of append, if you will, because you're adding another dimension. So for
Right.
wavelength 1, you have a MUA, MUS,
Right.
that sort of
Because
thing.
as that vector gets big, the computational complexity goes very high.
Exactly.
And Simplex is kind of not able to handle that.
Well, I'll go over
Okay.
Simplex. Yeah, I'll go over Simplex. You're exactly right, though. You fed right into my next chart in that one of the problems here is that you're sampling a lot of the numerical computational cost of this is high because depending on how many, you start with n parents and then you have to reproduce and then evaluate chi-squared all over this map. So lots of numerical evaluations of the model function, and you can see how it can kind of boom. Like the mutation portion can actually cause you to expand your location of searching, and so it can expand your domain, and that could be a problem too. Oh.
So kind of just looking at the chi-squared equation.
Yeah.
So let's say my measurements, the difference between my measurement and my model is pretty small, right, for each measurement. But then the standard deviation is high for all of them. So I don't know, to me this seems like it favors high standard deviations of my measurements.
Well, if the standard deviation is large,
Yeah.
that for that particular measurement,
Right.
then that particular
Point.
difference is going to be
Weighted.
weighted smaller
Right.
in the overall sum end. Is that?
I get that.
Okay.
But then isn't the point to minimize the chi-squared value?
It is. It's just a way to relatively weight the contributions from all of the measurements. You can imagine like for reflectance versus source detector separation, there might be a larger standard deviation in the reflectance at far distal source detector separations, and it puts the measurements kind of on a more equal ground.
Yeah, I think maybe I can clarify a little bit is that if you have a measurement set where all your measurements have a large standard deviation, what will likely happen is that your chi-squared topology will be one which is very shallow. And in these optimization algorithms, typically you can not only get the predicted value, but also an uncertainty to that value based on how far away from that mean value does the chi-square increase by a certain value. And so what will happen is that the uncertainties in your converged value will be very large, and that will be an indication of the fact that your measurements are poor. Does that help? Yeah. Is there?
think this is this is something that I'm not familiar with, the scaling variance with the chi-square. From what I know about chi-square is that you're assuming a function, and usually the variables have the same uncertainty, and they're normally distributed about that. You know, the function is unbiased, and you use that to determine the goodness of fit, and there's a critical cutoff that says that this function is the right function or it is not. This is a different application. This is kind of beyond my experience. And I think when you have all these different variables that have greatly different variances, it looks like maybe the variance correction is trying to bring them back towards normality.
Yeah, put them on the same playing ground. I want to reiterate, though, that you don't need to have this in the chi-squared equation. This is what they call the weighted, but the unweighted is the same equation without the denominator, and that can be minimized as well. In fact, in MATLAB, I think they have an optimization routine, fmin search, and it's formulated without the denominator here. So yeah, there are definitely optimization methods that utilize the unweighted.
Another way one can think about it is that if you have a series of measurements, 1 through m, and a few of those measurements have a really small variance, you know those measurements really well. If your converged optical properties really result in a deviation from that measurement, it's going to penalize you big time in that chi-square. Whereas you can be far away, if your converged optical properties are far away from a measurement that has a huge standard deviation, it's not going to hurt you that much. So it's a way of making sure that you pay the price for selecting a set of optical properties that is in large deviation from a measurement for which you have high precision for, or high confidence in.
I also think, going back to the previous question, why not use absolute value? And I think it goes back to the properties and the favorability of a maximum likelihood
Yes,
estimator, which is superior to any absolute value.
That's right.
estimate.
That's right. It falls out from that.
But I think that depends on the problem, right?
Under the assumptions.
Yeah.
Superior.
Under these assumptions, superior, but as you know, these assumptions are rarely correct for what we do.
Yeah, but the formulation of the equation comes from those. Yeah, right.
But I think we charge forward with these assumptions like they're true. Let's maybe step back and say, wait, hold on.
Yeah, maybe they're not.
So there's a broader field of measurement theory that is out there that actually you can come up with various formulations for your chi-squared estimator based on, you could assume, well, if you have Poisson statistics instead of Gaussian statistics for your measurement. And there's a huge field. You could take courses on formulating these estimators based on, modifications in the independence of your measurement set or different measurement statistics by which your measurements obey. So this is one metric for one set of assumptions, but there is a larger field that allows you to derive alternate metrics, as needed.
Okay, so here's the simplex method. This is what was used behind the scenes when you solved your integrating sphere. A simplex is kind of a geometric shape, and for the simplicity, just so we can visualize it, it's one dimension greater than the parameters that you're seeking to find. So let's say we're looking for 2 parameters. Then the simplex is a triangle. If you were looking for 3, it would be a tetrahedron. Is that right? With the triangular faces. So you set up your initial set of vertices. So for simplicity, let's just say that's a triangle. And each of the vertices represents a vector of the, so for instance, we're looking for mu a and mu s prime. And so there's we would have 3 pairs, mu a and mu s prime, representing the vertices of this triangle. And you would evaluate the chi-squared value at each of these vertices and order them. And then you would take away the top one, and you'd find the center of gravity without that top one. So if you have a triangle, you're actually finding the center of gravity along one side. Yeah. Yeah, I can't see my hand, huh? So you take away, say you take away this one, then you're looking for the center of gravity along this line. And I think, yeah, we called that V naught. And so you first check to see if you reflect. And you actually, there's a parameter alpha here that's used in which you reflect this triangle. And you determine, so that allows you to see, determine another vertex over here, and you determine what that chi-squared is at that reflection point. And if it's greater than your second to the largest chi-squared value, then you contract. And contract is a way of actually shrinking the triangle and creating. So basically, these reflection, contraction, expansion, reduction are ways of manipulating the triangle either through flipping or contracting. I'll show you a picture here that may be. So you start with a certain triangle, you find the center of gravity, and then you reflect, and this is your new triangle. Or you might contract, and then again using the center of gravity. Or this is a reduction, or this is an expansion. And here are kind of typical values of those coefficients in these different actions. This code is oftentimes called amoeba. Numerical recipes in C calls it amoeba because you can kind of picture there's this like triangular region that's kind of morphing and finding its way to this minima. But you have to be careful where you start your triangle, how big it is. You could pick a really small triangle and just kind of morph around in a little space. So you have to pick your simplex large enough that you're kind of sampling the more global space. And negative of this method is that it can stop when the derivative is not zero. So, well, that's probably the gradient-based group's criticism of it, because they say we can keep going because we have differential information. But your solutions yesterday showed that I think it worked quite well in the code, and Scott Prahl would not have used it unless it had produced good results. So now I'm going to move on to gradient-based. That's kind of a segue. Why you would want to know the derivative of the function and why that helps you solve inverse problems. So to motivate that, I'd like to describe the Newton-Raphson method. This might be a method you had in a numerical analysis class in which you're trying to find the roots of an equation. You start with an initial guess, and then you evaluate the function that you're trying to find the roots of, and then you take the derivative, and you find where that intersects with the y equals 0 x-axis here, and then you determine the function evaluation, and you keep on going until you find the root of this equation. The way that you update the parameters is that you take the previous parameter and you subtract the function evaluated at that previous parameter divided by the derivative. And so for a general update, for any step n plus 1, you take the previous n, you determine the function divided by the derivative at that n. So in concept, when applying this method, we're trying to minimize the gradient of chi-squared. The gradient is the derivative of the chi-squared with respect to all the parameters that you're seeking to determine. So it's of length p. And if you look at the form of what this gradient is, you just take that chi-squared and you differentiate it directly with respect to the parameters, and that's how you get this gradient here. So we need to take the derivative of the gradient, and so we find the Jacobian. And this is a p by p Hessian function, so you might be familiar with a Hessian where you take the second derivative with respect to the parameters. Along the diagonal is the second derivative. On the off diagonal, you have the cross derivatives with all the parameters. And likewise, determining what these different Hij's are just taking the second derivative of that chi-squared equation, just nothing complicated there. We write the update in matrix form is that you have the vector A at step n plus 1 is the previous vector minus, this is the equivalent of the function divided by its derivative. It's the Hessian inverse, and you multiply that with the gradient. So that's the kind of the Newton-Raphson vector equivalent. So Levenberg-Marquardt combines these two methods, the steepest descent, which is used far from the minima, and an inverse Hessian, which is used near the minima. And I'm just rewriting that a matrix A is 1/2 the Hessian, beta is negative 1/2 the gradient, and you can rewrite equation 8, this equation, this vector form here, matrix form, in kind of an AX equals B form right here. So it's a substitution of variables here. And this can be solved for this delta A. This is what you're looking for. Now the twist that Levenberg-Marquardt does is that it hits the diagonal with this 1 plus lambda. Lambda is always greater than 0. And it does nothing to the off-diagonal elements. And what that does, let's see if I show a representation. So yeah, so along the diagonal you have this lambda. Here's what you're looking for. Here's your B on the right-hand side. And so you're hitting this diagonal, and there's a starting point. And I've used this algorithm fairly well with this starting value of lambda 0.001. You compute what your chi-squared is at your current iteration. You set this lambda. You solve for the step. You evaluate what chi-squared is at that step. And if it didn't reduce chi-squared, you hit lambda with a factor of 10 and you try it again. If you did reduce chi-squared, then you undo, in a sense, you reduce your lambda by a factor of 10 and you update to that update and you go around. And you converge if the value of chi-squared is under a certain epsilon that you're looking for, or if two successive iterates are less than some epsilon. In fact, you're not improving what you're doing. So one of the pitfalls of this method is sometimes you can, because it's always looking to go downward, you can end up in a local minima. Simulated annealing allowed you to get out, but this is always trying to reduce. But one way to mitigate that, and one way that Boston's lab has used successfully, is you initiate several random initial guesses, and you see how, and use the Levenberg-Marquardt to find the minima, and then from that, I think we used 10 actually initial guesses. From those 10, you take the majority of where the minima and determine your parameters. Oh.
Hi. Can you, I guess, comment more about like the choice of lambda?
Yeah.
So wouldn't it, I guess, depend on those values? Because would you want like a percentage of, I guess, those values along the diagonal, or are you just adding like a specific absolute value to them?
Yeah, so it started out, that algorithm started out at 0.001. But if you didn't find a minima at the delta A that you were looking for, you hit this with a factor of 10. So now you're at 0.0001. And then if you don't, you hit it with a factor of 10 again. And I've seen this get up to 10, 100. Basically, what you're doing is you're making this matrix be diagonally dominant. You're trying to weight this far higher. You're moving to a matrix in which these are magnitudes larger than the off. And if you can think of it as like, say in the ultimate scheme where they're all 1 and the rest are 0, then you'd have the identity matrix, and that's invertible. And that's how you're able to get to an iterate that will move you around chi-square space. So yeah, these are, the nature of the algorithm allows these to gain in magnitude, and it allows you to emphasize that diagonal thing. As you get closer to your minima, you actually see that the multiplication of that lambda doesn't happen. You're actually going to a state where this is fairly small when you're close to the minima, and you're actually just inverting the Hessian.
Okay.
Yeah.
Thank you.
Sure. Thank you. So any other questions? I'm going to kind of shift gears and go on to a stochastic inverse problem using PMC and DMC. So I'll continue on unless there's any. Oh.
I was trying to like understand a little bit better, and it kind of looked like solving for like the moment of inertia to me. I don't know if you dealt with that kind of thing.
I'm not familiar with moment of inertia. Sorry.
It's okay. It just looked like that to me, so I was saying if it's similar, then it helped me understand. But I don't know.
We actually, in optical tomography, a kind of similar process is used, and maybe that'll help hit it in a different way. So one of the things, we've discussed how great Monte Carlo solutions, they can handle any geometry, small source detector separations when scattering and absorption on the same order, and for very complex tissues. So there was a desire to try to solve an inverse problem using Monte Carlo solutions. But Monte Carlo solutions can take a long time. And if you're putting it into an iterative method, the inverse solution is going to be unwieldy if you had to run a Monte Carlo solution every single time you updated your parameters. So we came up with first talking about the forward solution, something called perturbation Monte Carlo. And this allows the generation of any number of forward RTE solutions that are derived from a database of baseline biographies, random walks that were based on a baseline set of optical properties. So say you had the baseline set of optical properties A here. You could determine this model function prediction based on these properties by evaluating a random variable. That Greek letter C is a random variable. Evaluating that, and there's some measure theory here, but suffice it to say that the random walk process, the determination of intercollision distances, angle deflection, and such, are based on the optical properties of the background or the baseline. So say you wanted to figure out what is this model function at a changed set of optical properties. One way you could do that is you could determine this model function at these perturbed properties by running another set of random walks, another simulation. You could take the optical properties A plus delta A and use those to define your intercollision distances, all your, deflection and all that, and evaluate that. And that would be an independent simulation and take time. Instead, what we do is we use the simulation based on A, not A plus delta A, but we weight this random variable in an appropriate way such that the end result is an unbiased estimate of the perturbed system. And this weight here is something we call the radon-Nikodym derivative. But just think of it as maybe a Jacobian, a change of the random walk process due to the perturbed optical properties divided by the baseline. So that reweighting saves us a lot of time. We can create a database of background optical properties on random walks, and then we could read that in a post-processing way and apply a delta A to any change in any optical property and determine what our model function is. So it saves time. In addition, it also allows, because there's correlation in the perturbed results with the baseline, that this enables smaller relative uncertainties than the independent simulation. So there's a double bonus here. Not only am I saving time, I'm getting smaller relative uncertainties. In addition, we can differentiate that perturbed estimator with respect to any of the parameters we're looking for and feed those to a gradient base. And those derivatives can be determined by post-processing this database. So they're determined in a very fast way too. And keep in mind that you can you could segment the tissue, each of the regions could have different optical properties, and you could turn on perturbations in any one of those regions or combinations of them and determine what the model function is due to those changed optical properties. The difference is that it's a perturbative method. So it works best if that delta A is small. And if that delta A is large, then the variance in your perturbed estimate can get unwieldy. But just to give you an example of kind of numbers on this, we applied it successfully to a cervical layered tissue. US prime over mu A is about 20. G is 0.9. We have an L star of a 1.6. And the top layer was about a third of an L star. Note that if standard diffusion, there is a solution for a layered tissue, but that upper layer has to be greater in thickness than L star for that solution to apply. So we're outside that range in which you could use a diffusion solution. And we found recovery of mu A in about a third to 3 times the baseline and about plus or minus 30% of mu S, just to give you kind of ballpark of the when I say large perturbations, what the realm is. So, like I said, we take the background optical properties, run random walks, run simulations, store them in a database. In the first iterate, this delta A is 0. We determine the model prediction. We compare it with our measured data. We determine chi-squared. If it hasn't converged, we determine, using the derivatives, what delta A is, and then we update and cycle around until we have converged to a delta A that best matches the measured data, and usually that's when 2 successive iterates are less than an epsilon. So, I'm going to shift gears again. Any questions about PMC or DMC? David.
Thanks, Carol. I hope this is a good question. For PMC, you said it's a perturbative method. The absorption weighting component of the PMC operator is the continuous absorption weighting operator correct? Or it can be one or the other, but it seems like that's not a perturbative operator. It's really the change in the path lengths that's the true approximation. Is that correct?
Well, you can apply PMC using continuous absorption weighting. You can also apply it to discrete absorption weighting. And this weight factor is different for those two methods, because in continuous absorption weighting, your path lengths are based on mu s e to the minus mu s distance traveled, and discrete it's mu t e to the minus mu t distance traveled. So these ratios are going to have different forms for the different types of background. So it's based on whatever you ran your background simulation.
Okay, but that operation of the changing of the absorption is not approximate. Would you agree that it is? It doesn't require you to have a small delta A. That operator will work over large changes in absorption.
In absorption, yeah. Well, yeah, absorption, exactly. Absorption, as you saw from the cervical data, we actually recovered absorption with a far greater extent than scattering. And yeah.
So I think that's correct, more so if you're using a continuous absorption weighting situation where, the photon trajectories are, the geometrical configuration of the Monte Carlo trajectories are only linked to mu s. But for instance, if you impose a discrete absorption weighting in Monte Carlo and you do a mu a perturbation, you're not only changing the deweighting at the collision sites, but you're actually expanding or contracting the photon path lengths. And in that case, because it's linked to mu t, and then it becomes important what the relative magnitudes of mu a to mu s are, because then that implies a different expansion or contraction of the path lengths in the Monte Carlo. So when you perturb absorption, say within a context of a discrete absorption weighting algorithm, it not only changes the deweighting, but it also changes the geometrical net, or have you say, of the actual photon trajectories, whereas in CAW it does not.
So DAW is not statistically unbiased with respect to absorption?
It is, but I think what David's getting at is with continuous absorption weighting, it's an application of Beer's law, essentially. You're figuring out the path lengths in each of the regions of interest, and if there's varying mu a, you can apply the change to mu a in a very direct way and get the resulting perturbed reflectance or whatever measurement. But the DAW has a little different situation than that. So yeah, they've got different ratios due to the fact that the path lengths are based on mu t versus mu s. Yeah.
But they're both unbiased.
Yeah, they're both unbiased, for sure. Okay, I'll move on to optical tomography. This shows an example of a measurement device from Brian Pogue's group. I think there's somebody here from Brian Pogue's group. Yeah, so you've probably seen this in person.
I haven't seen this one yet, no.
Oh, okay. I got this from the Dartmouth Medicine magazine, the winter 2007. But it was a better picture than I had from their paper picture. Was kind of boring, and this was a lot more interesting looking. They have 16 sources and 16 detectors in an array here. A woman lies in prone position, and her breast is lying within this region here. So there's 215 measurements that surround the breast. And here shows some examples. I think this is a phantom that shows what the true distribution of absorption and scattering are, and then what the recovered optical properties and distribution are. So now we're determining a 3D spatial map of parameters, a lot more complicated problem. So now the minimization of chi-squared adds in this additional summation over the S sources, and you have S times N measurements at the tissue surface. And again, we're trying to minimize this with respect to a particular set of parameters that best match the measurements. So these parameters, though, describe the distribution or the optical properties of the light field in a segmented tissue. And so this number P is often greater than the number of measurements. So this is an underdetermined system and means it's ill-posed and regularization techniques are applied. In the examples that I was reading in Brian Pogue's group, they're segmenting the breast into 400, 1,000 different regions, and they're looking for the optical properties in each of those regions with 256 measurements. So you can rewrite this equation in matrix form, where this capital Y hat is the measurements. Here's the model approximation, and this produces the chi-squared value here in matrix form. Now there's a linearization that they do. They take the derivative of that equation and they set it to 0, and they ignore higher order terms. So there's going to be an expansion in delta A. So they're just taking the 0th term and the delta A term. There's a delta A squared and something, delta A cubed, and they're truncating that series. And in this equation, J is the Jacobian. It's the derivative of the model at all detectors for all the parameters. So it has dimension S times M, the number of sources times the number of measurements, detectors, cross P, the number of parameters. And if you solve this equation for delta A, you get something that looks like this. Notice that you have the Jacobian transport Jacobian, and you're trying to take the inverse. This is where the problem lies. And so what Brian Pogue's group has done is added this Tikhonov regularization. Notice that again along the diagonal, they're adding this lambda, and that's its purpose is to emphasize and make that matrix a lot more diagonally dominant. This regularization factor could be scalar. In Brian Pogue's group, I think they did it as a function of the tissue location. And you can find this inverse with this regularization using Levenberg-Marquardt, or sometimes people just try to invert this directly. So any questions about that before I move on to some examples of actual case studies in which we try to actually invert real data using an optimization method?
Carol, I know you've just discussed a number of methods going from simulated annealing to simplex to gradient-based optimization to genetic algorithms. And so I'm just trying to get a sense of, I know often the approach you take is very problem specific, but are there any generalizations on maybe situations of why, where the relative strengths and weaknesses of these various techniques are? Or is that something you may address towards the end of the talk? Or? Not really.
I mean, I've kind of after each segment, I kind of described what the pluses and minuses are, and it's true. It is problem specific. I think even within your lab, we started using Levenberg-Marquardt, but some of your students considered the genetic algorithm. I think they're viable options if you're having difficulty. MATLAB provides a Levenberg-Marquardt algorithm, which makes solving the inverse problem a little easier for your average student who's familiar using MATLAB. Using some of these other algorithms, you might have to code it up yourself. But I think they're viable, especially if you're finding difficulty resolving the inverse problem with the method that you're currently using. Yeah. But each one has its pluses or minuses. It's hard Hard to know. I know for me, I always go to Levenberg-Marquardt if I can. And most of the time you can, because the way MATLAB does it is actually, if you don't have differential information, it creates it for you in a finite difference way. So that's the go-to for me, at least, to solve something. But you know, like I said, it's problem dependent. You could run into a problem where it's not, it's getting stuck.
How about a mixed stochastic gradient method, like an extended common filter?
I'm not totally familiar with that. As far as a method to optimize and find the solution, I'm sure.
They're kind of touchy, like you were talking about setting the parameters. They're kind of touchy. I used them to train neural networks, which is a few parameters there. But they basically what happens is the covariance matrix starts out large and it collapses as success as the residual errors drop. If it doesn't reach if it gets stuck in a local minima, it'll blow up the covariance matrix again and jump out of the local minima and then collapse again. It's kind of, like I said, it's not something you'll turn somebody loose with, but if you were if you were using it yourself, you'll become familiar with setting, like forgetting parameters. There's a window where it de-weights past, because it's a recursive method, so it adds all the data together, but you can use a lambda parameter which forgets, has a weighting profile with time.
I see.
So as you can go along. I know that when you're making your software, you're trying to make it useful for people other than you, so that you don't have to tune it too much.
Yeah.
That's I think I found that it got much better convergence of weights than, say, a Levenberg-Marquardt.
I see.
Okay, but it's one of the ones where the person using it has to understand the response of the optimization method.
Yeah. The human becomes part of the optimization.
Yeah, where you're saying it's become unstable, so I got to collapse it down again, make the forgetting a window longer, and not
interact.
allow this covariance to blow up too much. So, but that's one of the things that I thought. My thesis advisor did a lot of common filtering, but I think it has both elements of a Jacobian, or actually a Hessian, an estimated Hessian, and also a stochastic component.
Thank you. So I thought we could look at some examples so you could see what an actual, instead of these schematics where I show cartoons of what's going on, what the actual chi-squared space looks like in certain problems. And look at the type of measurements, the location of these measurements, the effect of your inverse solution with respect to noise, and your initial guess. And in all of these case studies, I used the Levenberg-Marquardt. So let's look at a case in which we're looking at spatially resolved reflectance. I have 6 equispaced detectors at 0.1 to 0.6 millimeters away from the source. I'm going to simulate my measurements using this thing we call NURBS, and I think might be the first time we're talking about NURBS today. NURBS is non-uniform rational B-splines. We have a solution in the GUI on the forward analysis panel. There's a pull down, and we have a couple standard diffusion, and then we have a couple of NURBS solution. And what has been generated in NURBS is that Monte Carlo has been used to run a baseline set of reflectance measurements at a given set of optical properties. And actually it's Keenly who wrote the first paper, I think, on how if you change the optical properties, how you would adjust what the reflectance is. This is for a homogeneous tissue. And so you were able to, through this one baseline simulation, determine what reflectance is for varying optical properties. Then what this is a student that worked with the VP, Michele, and VP group worked on, is that we found that actually extending Keenly's method, in which you have bigger bins for larger rows and times, worked out better to get better estimates for those distal detectors, and then also applying a B-spline to the data to smooth it out was improve the results too. So these NURB solutions are nice because they're Monte Carlo solutions, very accurate, close to the source, at short times, and times in which the standard diffusion doesn't apply. So whenever I'm using the GUI and I want to use them, simulate measurements, my go-to is the NURBS, because that's closest to reality. In this case, we're going to try to fit that measured data with standard diffusion, with the point source. And we're going to look for, because standard diffusion's parameters are mu a and mu s prime, we're going to try to determine those. Now I know what the measured values are because I'm simulating the measurements, and I'm setting mu a to 0.01 inverse millimeters, mu s prime to 1. We have a mu s prime over mu a of 100. We're well within the diffuse regime as far as optical properties go, and we're going to invert and find out see if we can find these measured parameters using Levenberg-Marquardt. So here's a picture of what happened. Here's the initial guess. It's 0.05 for mu a, 1.2 for mu s prime. Here's what's the measured. Here's what the Levenberg-Marquardt converged to. It found 1.833 for mu a. Terrible. This is the error. And then mu s prime, here's the error. Here in blue are the measurements. Here's the initial guess, and then this is where the converged value is. And if you look at chi-squared space, so here's your mu a, mu s. These are iso curves of constant chi-squared. Here's where it started in the initial guess, and here's the path through chi-squared to finding this value of the converged value. But no, it's hard to see, but there's a blue dot here, and that blue dot here is representing the chi-squared value at the measured. It's actually not sitting in this trough. I also want to note that, so I entered this trough in this path, but as you enter, you can see that there's varying slopes entering this trough, and those will dictate how you enter via different initial guesses. So does anyone have a guess as to why I'm getting such a bad mu a recovery? And keep in mind, this is standard diffusion being used for your model problem. Oh, okay.
So that color bar represents the chi-squared
Yes,
value? Is that a log scale?
log scale.
Okay.
Yeah. Did you have a guess as to what's going wrong? No. Okay, let me hint. So notice that these source detector separation, L star in this problem is about 1 millimeter. And so this is 0.1 millimeter. First detector is at 0.1 millimeter. It's pretty close to the source. Standard diffusion needs to have the light field be isotropic, and so those regions are usually far from the source, where enough scattering events have occurred so that the light field is randomized. So one of the problems in choosing this selection of source detector separation is that I'm using a model that's not appropriate for this type of measurement. So let's move the detectors out. And let's make them be 1 to 6 L star, same number. And now you can see that the recovery is a lot better, definitely for mu a. Here's how I'm entering, same initial guess, but the chi-squared space is a lot different because of the choice of detectors. You can see that the measured data is actually closer to this basin here. And and so we've improved here. So this is kind of one of those cases in which you want to make sure whatever measurements you've taken, that your model function you're using to solve the inverse problem is relevant for that particular measurement.
So Carol, why isn't the measurement
Right in here?
lie at the global minima?
Well, you're still using standard diffusion. And I actually have an example where it's right in there, and I'll show you when that happens.
So primarily it's because your model is not perfect.
Your model's not perfect. So let's add,
Kind of related, so in the plot on the right, it looks like the converged solution is right on top of the measured on the left side there.
so here's the measured data.
No, not on the...
Over here?
On the reflections.
Oh, over here, the fit?
Yeah.
Yeah.
So that looks pretty darn good.
It looks good, doesn't it?
But the optical properties are still, 20% off.
That's right. That's right.
Yeah.
Yeah. Yeah. So it's looking good here. Looking like you're laying right on top, but it's the standard diffusion's attempt, and the optical properties it would need in order to fit that measured, and it's not.
Right.
Yeah, it's not perfect.
Yeah, and I mention this because usually we just look at, does the model fit the data?
Yeah.
And the model does fit the data.
Yeah,
But you can't trust what...
that's
comes out
right.
of it. Yeah.
That's right.
We hit that every day, we encounter that problem.
Thanks, Tom. That's good. Some real life experience. So let's see what happens when we add 5% noise. You can see that we degraded the recovery a bit in both mu A and mu S prime. It's still looking like it's finding a minima here, but this noise is adding to the ability to recover those optical properties. And so I tried another initial guess just to see how entering this basin would come from a different direction. And so here's another initial guess. I chose mu A to be 0.02 and mu S prime to be 0.8. And it shows this path. It's funny, it converges exactly to the same value. The convergence error is exactly the same. So it's a pretty strong trough right there. And then just for fun, I was trying to find a way to actually that it didn't converge to the same. I was trying a variety of different initial guesses. So I tried mu A of 0.1 and a mu S prime of 2. And I just included this just because I thought it was interesting. It's kind of wacky how it found it. It comes along here. It comes to this side of the trough. It goes over here. That's the derivative information kind of shooting you across. And this is also where, far from converged, we're using the steepest descent method, and it's kind of jumping a bit. Comes back here, jumps over here, and then it starts finding it in and goes right to that minima. But I included it just because it was a little wilder path to that minima, showing you kind of what the algorithm's trying to do as it's moving around chi-squared space. So now I'll shift to another problem in which we're going to try to find chromophore concentration using spatial frequency reflectance and wavelength dependence. So I've chosen these two spatial frequencies, 8 wavelengths in this range, equispaced. Again, I'm going to simulate my measurements with NURBS. I'm going to use my model function using NURBS too. Now this is the inverse crime. And they say, a lot of times people come up with models and you can never simulate your measured data with your model because you will create this inverse crime, and I'll show you an example of what happens. But we're trying to figure out what HB, HBO2 are, and A and B of the I don't write it here. Remember on the spectral panel, the scattering? Oh, right here, it's power law. A lambda to the minus b. So I'm trying to find these coefficients. So I'm looking for 4 parameters. And I took as my measured data using skin. I used these 2 concentrations for HP and HbO2. And I use these values so these are the values I'm seeking because they're in my measured data. And then I use Levenberg-Marquardt. Now, one of the things, so you're saying, gee, we were looking for mu A and mu S before, and now we're looking for these chromophore concentrations in A and B. How do you do that? Well, you just kind of expand your model function here. So now here are your parameters. From these, you determine what's your mu A as a function of wavelength, mu S prime as a function of wavelength, and then use your NURBS to do your model predictions, and then your measurements. This is your inverse problem. So it's just a matter of layering in this conversion, and you're still looking for these parameters on the outside of the model function. And I chose these HP and HbO2, but we could have similarly looked for other chromophore concentrations. So using this spatial frequency and no noise, look, we converged exactly to the right value. That's because we did the inverse crime. We used measurements that were derived from our model function. But you can see now that the actual measured data is sitting right in here. You're going right into that trough. And I just wanted to show you ideally what this would look like. And that's for the HB and HbO2 chi-squared space, and for the A and B, here's what it looks like. And again, we're going right in there. But this is the inverse crime. So let's add some noise to the measurements. Let's add 2% noise. We're going to still commit the inverse crime, but let's just add noise and see what happens. We add noise, and we had the same initial guess as the inverse crime charts before, but look what happens. We have terrible recovery of the chromophore concentration, and look what else happens. This is actually the initial guess down in the trough, and the Levenberg-Marquardt is actually moving you to this converged value in a very strange way up here, and that's why these recovery of these optical properties are so bad. Here's looking at A and B. Here things are better. Our recovery errors are a lot better. You can see that we started here and we're actually going into the trough. But can anyone guess possibly with this setup why the chromophore recovery is so bad? Now think of the fact that you have these spatial frequencies. And correct me if I'm wrong, David, but the larger the spatial frequency, the more shallow you're sampling the tissue. And so your path lengths in the tissue are shorter. If you went to smaller spatial frequency, you would sample deeper with longer path lengths. So one of the key things about absorption, finding absorption, I think you might hear more about this tomorrow from Vasan, is that you need path length information. You need long path lengths. You need long path lengths or long time to get absorption. And so this choice of spatial frequency compromised the ability to recover the absorption in this problem. So let's change our spatial frequencies to 0 and 0.2, and still with this 2% noise. And now you can see that the chromophore recovery is much improved. We're actually moving in the right direction to this trough. And for the scattering, they're still doing good. So this is another example of making sure that the measurement or the model that you're using and the measurements you're taking apply to the things that you're trying to recover. Absorption needs path length. So in summary,
Shouldn't that show up in the slope of the chi-squared space? Shouldn't that be, if you don't have enough, in this case, spatial frequency information, shouldn't all of the, the mu a's for mu s's kind of be together like, and David showed in his plot where at the higher spatial frequencies, you have no ability to discriminate that. Shouldn't that show up in how shallow the chi-squared space is?
I think what's happening here is this is pretty, I think because, Levenberg-Marquardt, the way that it's supposed to be working is finding differential information. And so, let's see, this is ranging from about blue to the red, so minus 3.8 to 4.1 on log scale. And if we...
Yeah, so this is actually quite shallow. So if you look at the dynamic range here, you're
sorry.
just half an order of magnitude, whereas in all the others, you're
Let's
going
look at
across
the one
and
here.
a half or 2 orders of magnitude. So yeah, you will see the shallowness of the chi-square.
Do we ever use that as a confidence metric in reality?
The Hessian actually gives you your confidence intervals. So, yeah, so from your Hessian, you can define your confidence intervals. So yes, exactly. The shallower, yeah, it's going to definitely affect your errors. So in summary, minimizing this chi-square can give you fits. I mean in the positive way rather than pulling out your hair, but I think that sometimes it does that too, definitely. You're like, what's going on? I say that in kind of tongue-in-cheek. I hope to have shown that, you want to make sure that your measurement is sensitive to your parameters of interest and that your model is valid for the measurement type. Gave you a little exposure to using a stochastic model for inverse solutions. This could be applied to complex geometries. And just a very superficial exposure to these different optimization methods. I want to note that the inverse solutions that I ran in the last 2 case studies are just a really simple extension of an inverse solution that we have example in this VTS solver demo that's in the MATLAB interop. So if you want to play with that, and if you're interested, come talk to me. I'll help you set up a problem in which you could actually use the software to run an inverse problem that you'd like to run. So thank you for your attention.